Now we are going to see an interesting consequence of Riemann-Stieltjes integral of f with respect to alpha when alpha is a function of bounded variation. Okay, and so far we discussed some consequences of Riemann-Stieltjes integral of f with respect to alpha when alpha is a monotonically increasing function. Okay. In the starting, while defining what is the Riemann-Stieltjes integral, we just assumed alpha is a real valued and bounded function alone. Okay. Next, we take our alpha as a monotonically increasing function, and then we define what is upper Stieltjes sum, lower Stieltjes sum, and what is Riemann's condition. So we discussed these things. Okay, now we take our alpha is a function of bounded variation, and then we see some consequences of this. Okay, to see this, first we should know what is a function of bounded variation. We need the basic definitions: bounded variation, total variation, and some characterization of bounded variation. But these things are not in your syllabus. These things are not included in your syllabus. But to know the important theorem, to understand the proof of the theorem, we should know the definition. Then only we can apply there. So first let us see what is a bounded variation. Okay, for usually anything if we define for a function, we denote the function by f. So we now we define what is bounded variation using the notation f. But while applying in the theorem, we will take our alpha as a function of bounded variation. Okay. Let f be defined on closed interval AB. It is f is a function on closed interval AB, and take a partition P of closed interval A comma B. And this notation we know well. What is delta fk? Delta fk is f of xk minus f of xk minus 1. And if there exists a positive number m such that sigma k equal to 1 to n modulus delta fk is less than or equal to m for all partitions of AB, then f is said to be of bounded variation on closed interval A comma B. Okay. So how to compute this one? First you find, now take a partition. With respect to the partition points, first we find delta fk. What is delta fk? It is f of xk minus f of xk minus 1. Okay, at the partition points, we find the corresponding values under the function f. And then in each subinterval, we find the difference. F of xk minus f of xk minus 1. And the difference may be positive or negative. And I told you already that if the function decreases, then the difference will be negative. Okay. But we don't want a negative value. We want only the positive value. So take modulus delta fk. Modulus delta fk means what? Delta fk may be positive or negative. If it is positive, take as it is. If it is negative, and take it as a positive one. So find modulus delta fk, and then do this for each k, and then take the sum. Okay, in each subinterval, we find the difference, and we sum up all the difference. Okay, and if this difference is less than or equal to m for some m. Okay, and this is true for every partition. Okay, find this sum with respect to every partition of the closed interval AB. Okay, take the other partition. With respect to the partition also, find this sum. But all the sums, okay, should be less than or equal to m. If such a number m exists, then we say our function is of bounded variation. Okay, so the name itself tell the definition. Bounded variation means what? Variation means the difference. F of xk minus f of xk minus 1, this difference. And bounded means the sum of all the differences is bounded by m. Okay, So to understand this, we denote the definition as, we call the definition name as bounded variation. Okay. So how to find this? You take a partition, the partition points, find the value of the points under the function f and compute the differences. Then take the modulus values of the differences and find the sum, and do this for all partitions and closed interval AB. And the sum should be less than or equal to m for sum m. If this is true, then we say the function f is of bounded variation. Okay. Now, if the function f is a monotonic one, then f is of bounded variation. Actually, this is an example of a function of bounded variation. If is monotonic means what? If is a monotonically increasing or monotonically decreasing function. Okay, whatever it may be, we can show that you just apply the definition of bounded variation. Then we can see that it satisfies the definition, and hence if is of bounded variation. Actually, this is very simple. Can do yourself. I'm not going deeper into this because these things are not in your syllabus. Just for understanding, I'm telling you this. Okay, next. And this one example of a function which is not of bounded variation. Okay. If you take f of x equal to 0, if x equal to 0, and f of x equal to 1 by x, if x lies between x is greater than 0 and less than or equal to 1. Okay, actually you can prove proving this is not a function of bounded variation. It's very simple because we are considering closed interval 0, 1. Our partition points, each point is of the form 1 by 2, 1 by 3, etc. 1 by 4, 1 by 10, like that. Okay. So, and we have defined the function such that f of that is f reciprocal the value of x. So if you take 1 by 10 means what? F of x will become 10. That is, if you increase the partition, if you increase the points of the partition, then definitely the value of f of x will grow. Okay, and hence automatically the difference will grow and the sum will grow. So it is not a bounded one. So the function is not. It's an example of a function. There are a lot of functions which are of bounded variation, and this is one such function. You try to work out this yourself. Now, next important definition of total variation. Okay, take a function of bounded variation. Bounded variation means what? Just if you find sigma k equal to 1 to n modulus delta fk, then there exists a number m such that this sum is always less than or equal to m. That means this sum is always bounded by some number. Okay, that is, the sum is bounded above by some number. Bounded above means what? Supremum exists. Okay, so find the supremum. Actually, we are computing sum with respect to each partition, and we know that in the closed interval AB, we are having many partitions. Okay, with respect to each partition, find the sum. So we will get a collection of sums which are bounded above, and hence the collection we can find supremum for that collection and find the supremum. We call that supremum as total variation. Okay. So, and the notation is VF of AB. Okay, this V stands for total variation of the function f on the closed interval a comma b. Okay, here just we put open bracket just as a notation. Actually, we are finding actually under discussion we are having closed interval a comma b, and here this is just a notation to denote total variation of f on the closed interval a comma b. Okay. Now this is a characterization of the function which is of bounded variation. The function f is of take a function f on closed interval a b. Then f is of bounded variation if and only if f can be expressed as the difference of two increasing functions. Okay, suppose okay, take a function of bounded variation, then we can write f as the difference of two increasing functions. Difference of two functions means what? We can write f is equal to f1 minus f2. Okay, and both the functions f1 and f2 are increasing functions. Okay, and the converse also true. If we are able to write a function as the difference of two increasing functions, then the function must be of bounded variation. So that's why we have given here if and only if. And I also not going to the proof of this theorem because it is not in your syllabus. Okay, but to understand our theorem, we need to know this. And this is very important. The representation of a function of bounded variation as a difference of two increasing functions is by no means unique. Okay, so we are writing f is equal to f1 minus f2, but this representation is not unique. That means we may have two more functions. Say for example f1 dash and f2 dash, both are increasing, and such that f can be written as f is equal to f1 dash minus f2 dash. Okay, so the representation as a difference of two increasing functions of a function of bounded variation is not unique one. Okay, next. Okay, now come to our discussion. We are discussing about the Riemann-Stieltjes integral of f with respect to alpha. Okay, now what will happen to our integral, and what is is there any important consequence if alpha is a function of bounded variation? Okay, if we take our function alpha is of bounded variation, now only we discussed that our function alpha can be written as alpha 1 minus alpha 2, and both alpha 1 and alpha 2 are increasing functions. Now, if f is integrable with respect to alpha 1 and f is integral with respect to alpha 2, then by the linearity property, we can show that f is integrable with respect to alpha. Okay, but what about the converse? Okay, first, suppose if f is integral with respect to alpha 1 and with respect to alpha 2, then applying the linear property, we get that f is integral with respect to alpha. But look at the converse part. Converse means, suppose if f is integral with respect to alpha, can we say f is integrable with respect to alpha 1 and integrable with respect to alpha 2? Okay, this is the question, but the converse is not necessarily true. Okay, so the converse is not necessarily true because because this decomposition, because suppose if we take f is integrable with respect to alpha and alpha is of bounded variation. Okay, now applying since alpha is a bounded variation, we can write alpha is equal to alpha 1 minus alpha 2, but writing like this is not unique. We may have alpha is equal to alpha 1 dash minus alpha 2 dash. Okay, therefore we cannot say if is integrable with respect to alpha 1 and integrable with respect to alpha 2. Okay, sometimes it may happen and sometimes it may not be true. Okay, and next question is, under what situation this is true? Okay, this is true when alpha 1 is the total variation of alpha. Okay, so what are we going to see? So f is we are given with the fact that f is integrable and alpha is a function of bounded variation. Okay, now we can write alpha is equal to alpha 1 minus alpha 2, and we can show that f is integrable with respect to alpha 1 and with respect to alpha 2 if alpha 1 is the total variation of alpha. And as usual, okay, anything we want in mathematics, we just take as it is. Okay, so just you bring alpha 1 this side, then alpha 2 can be written as alpha 1 minus alpha. Okay, So if alpha 2 is alpha 1 minus alpha, and alpha 1 is the total variation alpha, total variation of alpha, then we can show this. Okay. And this is the statement of the theorem. And we shall discuss the proof in the next class. The proof is very important. And in the proof steps, as we are going to apply the consequences of what is bounded variation and what is total variation. Okay, you remember the definitions. Okay, with this, I close this one, and the proof we shall discuss in the next class.